webinar about data collection and processing for the dynamic EPC. And my name is Michał Pomianowski, and I am coordinator of the E-DYCE project, which is about energy flexible dynamic building certification. The energy performance evaluation of buildings in operation requires today a collection of data from multiple sensors and meters. This is enabled by the most recent developments in IoT and BMS system, as well as open source databases. Once this data is collected, then it is analyzed in order to provide the value to the building owner, manager, or just the tenant. Today, in this webinar, we will share our experiences in E-DYCE project regarding the demonstration activities, monitoring activities in the buildings that are part of the project. Today, we have prepared for you 6 presentations, 10-minute presentation. This is the first one. And after me, we have my colleagues with me who will present their experiences. The first after me will be Tristan from Estia, which is a consulting research company based in Switzerland. And he will share with you his experiences with work from EPCs toward DEPC, so Dynamic Energy Performance Certification, related to monitoring of energy and indoor climate and performance gap analysis. After Tristan, we have Pierre from Neogrid, which is the energy optimization company based in Denmark, and he will tell you about their experiences with the industrial setup of the monitoring infrastructure in residential buildings and their online platform. After that, we have Giacomo Chiesa from Politecnico di Torino from Italy, and he will tell us about their experiences in Italian demonstration cases, monitoring, and towards the modeling plans that we use in E-DYCE. After Giacomo, we have our guest speaker, Pedro Ferreira from Lisbon University, who is a coordinator of SATO project, where they work on the overall self-assessment of buildings and their energy optimization. He will also share us their experiences related to the monitoring activities in the project. And the final presentation will be given by Dimitris Lokas from CORE, and he will tell us about E-DYCE prediction capabilities and their own CORE cloud hybrid infrastructure. Yes. Now, I would like to move to a short introduction about E-DYCE project, what it is about, and then afterwards, after that presentation, my colleagues will present. So E-DYCE is a consortium that consists of 10 stakeholders that are based in 4 European countries, and we are one of 13 projects that have been funded to work related to the improvements of energy performance certificates, also the future assessment of the buildings. So currently there are 13 of these projects, and some of them has finished this year, and some of them are finishing next year, while at the same time, some of the projects are starting right now. So this is a process. For E-DYCE, what was our motivation? Well, the main motivation for this project was the performance gap, which is about, there is a difference between the theoretical consumption we expect from our calculation and modeling and the actual energy performance of buildings. What we can see from the data that has been collected over the recent years is that buildings, especially the new one, underperform comparing to our predictions. And the buildings that are old usually overperform comparing to our predictions. The actual consumption in the new buildings is usually higher, and the energy use in the old buildings is usually lower than we expect. The reason behind that is multiple, but to make the long story short, there are two main components. The first one is that, first of all, our calculation methods are simplified and they are not able to capture the real operation of the buildings. The second main reason that stands behind the performance gap is that the building is used differently than our assumptions. So building users, occupants, are using it in a different way than we engineers would expect it to be used. Related to this performance gap are also issues related to the renovation cases. If we look at the old buildings, so that would be fall into class F and G, that would be energy renovated, then we can see that our theoretical expectations or the theoretical calculations are very optimistic, while at the same time, the actual savings are much lower. This creates a question: how valuable and reliable these calculations are. In the long term, if we continue the way we do today, we risk that our clients, building owners, will not trust the calculation and methods that we use today. So we have to do something about that. Then, couple of words about E-DYCE objective and key results. Well, the main objective of the project is to develop a methodology for dynamic certification of building that is based on both dynamic modeling and feasible monitoring. This is the part of the focus of today's webinar. The second objective is to develop integration framework and also methods to facilitate modeling. Here, we work with a middleware solution that is bridging the monitoring solution from the building. And at the same time, we work to develop a pre-DYCE tool. This is a tool to facilitate modeling process. The third objective is related to the accurate and clear feedback and also to propagate awareness of the building operation. This is done by developing E-DYCE protocols for end users that collects a predefined KPIs, so key performance indicators. At the same time, we also develop renovation and operational roadmaps. The fourth objective is to achieve optimization of building performance. This is done by reducing the performance gap, achieving operational savings, and propagating free running operation of the building, which is minimizing the mechanical systems to run and propagating the passive solutions. These all objectives are to be demonstrated and applied in the demonstration environment, which are the buildings that we use in the project and where we are implementing our developments. So here you can see the overview of the demonstration cases that we have in E-DYCE project. We have demonstration cases, 4 of them in Geneva in Switzerland. We have 5 buildings in Italy, in Torino. We have 3 buildings located in north part of Denmark. We have 1 building in Nicosia in Cyprus, and we have also a slightly different case, which is a district case of Geneva, where we look at the bulk of buildings. So by having these buildings located in different climates, we cover actually quite large share of different climate possibilities and also building typologies. Now, my colleagues will continue their presentation looking at some of these buildings and showing you how the monitoring approach has been solved and what kind of experiences we have gained over the last 2 years of work of E-DYCE project. Here, I would like to stop my presentation and pass my voice and the floor to Tristan. Thank you very much.
Hi, everyone.
Good morning, Tristan. Are you ready?
Yes, I am. Thank you. As Michel presented, I'm Tristan from Estia, a building physics company in Switzerland. And here I'll present you the monitoring in Switzerland and how we try to go from EPC to DEPC. So first, what is a monitoring? As you can see here, you can see a smartwatch and how it renders on a smartphone, and then you can compare it to a building. So you want to observe a survey defined quantity over time. The important aspects here are the quantity you want to survey, the fact that you observe it over time, and the fact that you want to see it visually. So again, when you compare the smartwatch with the building, here you have a lot of information, the number of steps, your heart rate, and everything. And when you look at a building, usually you don't have that many information. You don't know how much energy it consumes. So why do we want to monitor the building? Like when we run, we want to know how many energy we consume. So you want to assess the energy consumption and you want to see if there is a performance gap, like Michel introduced. We also want to calibrate the dynamic simulation models for the building because we want to go from a static EPC to a dynamic one. In the real life, we would like to follow also the energy consumption, and we will also like to identify the drift causes by following the indoor conditions of the building. And we can, if we have a monitoring that is thorough enough, evaluate the optimization actions. How do you want to compare what you measure? First, you can compare it with the EPC, so the standard energy performance certificate. You can also compare it with the past performances of a building, or you can compare it with other buildings within a building stock. Also, we would like to see if you can compare it with theoretical objective, being like a dynamic EPC. Then I'd like to show you the different possible monitored quantities in the building. First, the heat. You'd like to know how much heat you consume for space heating and for domestic hot water. Also, you would like to follow the electricity, so the user consumption, also the technical installations, how much it consumes, and if you have one, maybe the PV system. Of course, you can also monitor a lot of other information, but this is what is being important for our project. You want to also follow the indoor environment quality, or IEQ, and mainly the indoor air temperature for comfort and the indoor air quality, so you avoid having actions that are behaving incorrectly for the main users of the building. So now I have few monitoring examples and to see the panel of possibilities to follow mainly the energy. So first, I would like to present you the Geneva E-DYCE, which is the heat consumption index in French. And then I'll show you the building 1.3 that is located also in Geneva, and I'll show it to you before the project, what monitoring we implemented, and then what is rendering now. So first, the heat consumption index in Geneva. The canton of Geneva introduced a law that forces all of the owners of large buildings to enter the annual heat consumption of their building in a database. This database is the E-DYCE, or Heat Consumption Index. So you can access this database and you can see how your building is behaving from the beginning, mainly when they introduced the law in 1994. So this allows you to do a great comparison at the building stock level. Here, for example, you can see that this building, the 1.4 in Geneva, is behaving worse than the main multifamily house buildings in Geneva. Also, you can see the long-term evolution. Here, you can see that it's improving over time thanks to optimization actions. The issue with this is you have a long feedback time, because if you implement an action, you change your heater or something like that, it will take you several years to see the improvement. And the advantages on the other side is that it's pretty low cost because it's only a database and taking annual energy consumptions. On the other side, we have the building 1.3. This is a focus on one building out of the 4 that we have in Geneva, and I present it here to you. So it's located in Geneva. As you can see, it's in Central Europe, and it's a multi-family house building, which is pretty large. It was built in the 80s, so with a small insulation, and the total heated floor area is 10,000 square meters. So we focused the monitoring on one entry, which is central, so that it would be similar to the other entries. So before the project, we only had few data available, mainly the gas bills. So we also had the heat consumption index, but we focused on the E-DYCE to evaluate the performance gap. Here you can see the plots of the energy signature with the monthly gas bills, and we compare it to the static EPC signature. So you can evaluate the performance gap thanks to this monthly data, because you can evaluate that for a defined external mean temperature, you're consuming more on average than what is supposed to be on the static EPC. So this allows you to identify a performance gap. It is mainly cost-free because you're based on gas bills that are available, but it's available but hard to find. You would have to go either to the owner or the gas delivery company to get the information. Also, the other issue with this type of analysis is that you don't get any explanation for the performance gap. So we decided to install a monitoring on this building. And mainly, we installed a few counters. First, for the heat, we installed a counter on the domestic hot water production and on the total heat production from the gas heater. This would allow us to have both domestic hot water and space heating consumption, because the subtraction of the two would give us the space heating. We also installed counters for electricity to have the consumption of the heat technical installation as well as the ventilation, because in this particular case, we changed the ventilation system at one point and wanted to see the improvement. Also, to follow the quality of the indoor environment, we installed a movable gateway with 24 probes connected that we installed in the different rooms of the building. So this was great on the paper. However, we had several issues. First of all, we had a very large time of delivery because of issues coming from COVID and delivery time. Also, the installation took a lot of time, particularly for the heat counters. They had a great issue to connect everything. And this was very unexpected. And also the cost of the overall installation. So it was quite expensive. And this is one of the drawbacks of a thorough monitoring. It cost us 18,000 euros for the counters, the energy counters, and 13,000 euros for the movable gateway. So it's great, we installed this. What can we get out of this? So we can get hourly monitoring of the heat and hourly monitoring of the indoor condition, mainly temperature, relative humidity, and CO2. You can see here on the right, the heat consumption since the counters have been installed. And you can see that you can identify when the heating is starting. You can see that the total heat consumption derives from the domestic hot water production. And that allows us to see when the heating has been turned on. Also, we can see that when we changed the ventilation system, we improved the indoor air quality by comparing data from January to October. This is the CO2 level in the same room in 2 different periods. So we can see that changing the ventilation system allowed to have a better air quality. And we will also assess if this reduces the heat consumption. So the objectives of this monitoring was to evaluate the optimization action and to see it on a short on a short timeline. So we would have a better feedback than if we would compare the heat consumption index annually. Also, we can define the adapted condition of use thanks to the indoor temperature for the dynamic EPC. And the drawback of this is, of course, the cost of installation. To conclude, the monitoring is, of course, essential to evaluate the energy performance of a building. And the monitoring of the indoor environment quality is very important to both understand the performance gap and in the project to calibrate the dynamic simulation models for E-DYCE. Very important aspect is the time interval between the measurements gives you a good idea of how much time you would need to get a feedback. So if you have annual measurements, of course, you get annual feedback. And then the cost of and time of installation are very important these days, and it surprised us. So I just thought I should share that information. And of course, there are a lot of available technologies. And when you are handling stuff at the building stock level, it is difficult to harmonize and to have like proper comparison between one building and another. I'll leave now Pierre present his experience with the Danish case studies. Thank you for your attention.
Thank you, Tristan.
One issue before Pierre starts is that my colleagues has notified me that we have, of course, our guest here, and we would be very happy to receive questions from you. If you have any questions, please write them in the chat, and then we will address them at the end of the presentations. So after all of the presentation are ready, we will answer them. Another thing that we should notify you is that we are recording this presentation, so you should know that. Thank you very much, and Pierre, the floor is yours.
Thank you, Michael. So yeah, my name is Pierre, as said. I'm from NeoGrid Technologies, which I'll present later. And the focus of this presentation will be an industrial perspective on data collection and analysis in a multifamily residential building setup for, again, this dynamic EPC that we are talking about today. Very quickly, NeoGrid Technologies, we are a small company based in Aalborg, Denmark. We have extensive experience in research and development projects in the building energy sector, and we provide commercial cloud-based solution for data collection and control infrastructure, which mainly overlaps with what I'm going to talk about today, energy and indoor climate management systems. We do optimized control of space and water heating 24/7 in more than 400 buildings, so extensive experience on this level too, and online monitoring and full detection of HVAC installations. We are managing the E-DYCE demonstration sites in Denmark, which are 3 buildings built somewhere in between the late 60s and the early 70s, typically a size of 18 to 40 apartments with 1,500 to 3,300 square meters, so sort of medium-sized share housing. They were all renovated in the early 2010s, managed by housing associations, so people who live in those buildings don't own the buildings as such. It's managed by a housing association, which is important for the decision processes, and the heat is supplied by district heating. And those kind of buildings are representative of our main customer segment, which allows me to provide you some more insight than what we just learned in the course of the project so far. So let me start with data collection technology for dynamic EPC. A bit of overlap with what Tristan just presented before. What do we want to measure here? Essentially 4 dimensions: energy, the working of the hydronic system providing the heat, indoor climate, and ventilation parameters, if any of them is available. We essentially can look at 2 levels, both centrally and at apartment level. Basically, central measurements are rather cheap, but it's often not sort of granular enough to be able to have very specific actions, while data at apartment level is trickier to get and also more expensive, but can be a good complement. Looking at energy, basically at the central level, we want to know how much heat we supplied and how much electricity is being provided to the building. While at apartment level, we are interested in knowing how the heating demand is per apartment and what's the hot water flow, also to get the hot water consumption per apartment. When it comes to the hydronic system, so basically the hot water supply within the building, we want to know return and supply temperatures for both space and water heating to get an idea of specific faults that might be happening out there, and also potential optimization potential for the different set points that are being used. At apartment level, we also are interested in supply and return temperatures for the space heating, also because in a district heating context, the good balancing of the different heating systems within the apartments is critical to ensure a good level of return temperature and an efficient operation within the greater space of the district heating, as well as radiator settings, which we can, for example, get through smart thermostats. When it comes to indoor climate, that's specifically something that we look at at the apartment level, where we are interested in indoor temperatures, as well as relative humidity, CO2, and window opening when this is possible to get, and I'll get back to that. And then if ventilation is installed in the building, typically in those renovated buildings, some level of mechanical ventilation is implemented, then set point, electricity demand, and the supply and exhaust temperatures are of interest. All of those kinds of information we are interested in at sort of hourly level in terms of resolution are better, because we need high resolution data to be able to identify specific faults. As Tristan was saying, if we have very slow feedback, it's not so useful for the tenants because, or for the building owner, because it increases the time that they will have to respond to changes, but it's also reducing the possibilities of dynamic analysis on our side. How do we measure it? This is basically an insight in what kind of commercial technology we have. The simple message here is our strategy is interface to as much of the existing as possible, and then complete where necessary. Buildings have a lot of data that is found in, like a lot of data collection that is found in them already. And it's a bit of a shame to reinstall new sensors just because you're not compatible with the existing. So we as a small company chose to make a technology that could interface to most equipment possible before starting to extend it. From the left, you have some examples of small IoT sensors that were added on top of the system to get some measurements that were not available. In the middle, you have our box, this orange rectangle that interfaces to pumps, the regulation of the heating as well, via different interfaces that I'll be showing to you later. And basically just showing how we interface to the existing via specific communication protocols. And then on the right, the kind of sensors that we install at apartment level with wireless technologies that make a very flexible setup at relatively low cost. In terms of communication protocol to build on top of what I was showing before, essentially there's 3 ways to go. Wired protocols, where we are quite limited by the length of the wires that we can use, and that can be quite tricky to install in terms of the technician time that you have to use on them. Wireless protocols that are much more flexible in terms of where you can place your sensor and so on, where the limitation is basically on both the battery lifetime for some of the protocols and the range, which might require repeaters, as in, for example, wireless M-Bus. And then the last one in our IoT world is API integrations from cloud to cloud, which allow direct reuse of smart equipment, provided that we have volume enough to interface from one cloud system to ours. But that's becoming more and more popular with especially indoor climate, where a lot of services are found already. Looking at integration with existing services, because that's more or less the key to having a commercially viable DEPC framework where we collect data and exchange data. In E-DYCE, we've made the choice of relying on cross-platform integration. So as you can see from the left, you have the building with a gateway that talks to our preheat cloud. Preheat is just the commercial name of our solution, our cloud gets information from third-party databases, for example, weather data and so on. Then it talks further to MTech's FuseX platform. MTech is a partner in the project. And the FuseX platform is then able to talk further with Aalborg University carrying out some simulations, core, which you will see later, providing more detailed forecasts of a number of inputs, and then Politecnico in the Italian case that Giacomo will be presenting later. So the key is very much, once you have data, you have different actors, make sure that you share data between the actors. And on our side, sort of this preheated cloud builds on top of our control and monitoring solution. So it might not be just a one-off to do performance certification. It's basically a service that is already there where we unlock a new feature to be able to talk to a new platform. And in order to do this cross-platform exchange, it's important to think about this sort of cross-platform facilitation, as I call it here. At the moment, a lot of those platforms are very monolithic. Data is locked in them, often available within the environment, but not available to third parties. And that's the very tricky point. When you come as a third party who wants to provide a new service, that's you basically get a bottleneck there. And that is very much of a shame for the building owner, but also in terms of all the potential that you cannot unlock. And with our preheat system, we've made a design choice from early on that was coming from the research and development world, where we had a number of partners that needed to access to the data, that we have a fully documented open API allowing usage of the data with open source wrappers for Python and MATLAB, which are the tools that our collaborators use, which makes it very easy to interact with the open API, even if you don't have sort of extensive software knowledge of interacting with APIs, and where the data is structured in a source agnostic format so that you don't care what kind of sensors it's coming from. What you're interested in is that something is a supply temperature sensor, for example, connected to the heating system, or like the sort of very clearly formatted data format. And to finish this presentation, I would like to touch a little bit upon the challenges of data acquisition in buildings. There's going to be a bit of overlap in what we witness with Tristan, essentially global supply issues for sensors and meters. This has become very tricky in the post-COVID world with any kind of equipment that has to be shipped around the world or has microprocessors. The fact that we also need to take into account when we do some monitoring, that it's not only the installation of sensors and meters that is costly, but also that we need to keep resources aside for the maintenance of this data collection. Putting something in place and expecting that it's going to work until we take it away, that's typically not the case. Some resources have to be spent on maintenance. Interfacing to legacy equipment using old protocol where documentation has often been lost has been a challenge, at least in one of the buildings, with ventilation, and we have also some experience with other places where it was tricky to interface to the existing. In terms of market and services for the DEPC framework, it's something that is tricky out there is also that we transition from a deliver and forget business model where you send someone who looks at the building at one point in time, does an assessment, delivers the assessment report, walks away, to a service where we have an ongoing delivery of the service with running costs and so on. That's a change in the market that has to be taken into account as well, that introduces some challenges. And then very specifically to the multifamily built environment, we do have some bottlenecks with, among others, as many of you would expect, GDPR complexifying the landscape, where you have to collect consent per household with a difficulty to access the tenants, both in terms of prior information, because consent has to be informed, and then to get their agreement. And then you can also get issues of change of tenancy over time, where you have to get the agreement from one tenant to the other to continue collecting the data. And that a lot of the consent that is already acquired by the housing association is often usage specific and limited, for example, specifically for controlling or billing. And then you come with a new use case of performance evaluation or introduce new data processing partners that were not covered by the original agreement that make it difficult to reuse it. And you might have to get back to the tenants and spend a lot of time and man-hours in collecting those consents, which increases the cost of your dynamic EPC. And in this environment with housing association, we also need to get the contacts done via the housing association, which puts us in a multi-stakeholder collaboration setup, which also introduces some further challenges that are important to keep in mind. And that completes the talk from my side. You're welcome to post questions on the chat or get in touch and with the credentials here. Thank you, and I'll pass the floor further to Giacomo.
Thank you. Okay. Okay, so welcome to this presentation. I'm Giacomo Chiesa from Politecnico, and I will present, similar to my colleague, how we have implemented in the Italian demo cases monitoring and modeling plan for the E-DYCE project. As mentioned before by Michael, we have 5 Italian demo cases representative of typical houses and buildings that you may find in this type of municipality in which we are the demo, which is Torre Pellice, which is very representative of medium to low dimension municipality in Italy. If you look in this graph with all Italian municipalities, that's very representative in terms of medium cities, so not the big city. We have 3 single or double family house and 2 schools built in different periods. Especially one of the schools is very old, is recognized as a historical building, and the other is in the 70s with very small insulation, but it's bigger with 4 floors. Our main idea here is to translate you can say the rationale behind the E-DYCE approach shown by Michael in the first presentations into this demo, following this approach to defining the demo inspection. So first data collection, the final one to produce the dynamic energy model, and to support the monitoring plan and sensoring installation till arriving to have a series in the database in real time supported model verifications and after performance gap detection. So we don't see exactly how the platform for modeling is working. What we will see here is that the sensor that we have selected, how we have performed inspection, and how we arrive to the modeling and the model verification phase. In particular, we have 2 types of main sensor elements. The first one is a weather station cloud connected, positioned in one of the demo buildings that through REST API will connect to the project middleware supported by Fusion and partner, and to our local server in Torino University. In addition to that, we have a series of sensors with data logger and gateways supporting again cloud communications that through SOAP may be retrieved by again the project middleware, and so may feed automatically dynamic energy simulation to the real-time approach. Looking and using these 4 steps that we'll see today, so inspection, data collection for modeling, the monitoring and the model verifications, we will apply it now for simplification to one of the 5 demo building, which is the first mentioned. So a public school building in the 70s with 4 floors. What we found, like in several other demos, is that almost any information is available. None of these 5 buildings has a monitoring system installed. With the exclusion of this school, but it's not accessible. It's only managed by the company that you can say remotely control the heating solution. That is a small district heating, so in reality it's also served in other buildings. So the installation of the sensor and the collection of data has all been done during the project. Also in terms of static energy certification, this has been produced in almost all cases. So we make a typical inspection as a relief. The production of the CAD drawings were not available till the production after the 3D model that has been passed to the Energy Plus modeling approach. We also collected the tailored positioning of solution and system in the buildings to feed the static APC, for example, in the school lighting consumption is required. In addition to that, we have very short-term monitoring to detect the sort of general U-value or starting U-value passages to confirm what we get by Tabula example or by other databases existing locally. And in addition to that, in the school cases in particular, we also have an inspection in walls in which we know what it is because we have installed a detached ventilation system for the project. A very good chance considering that COVID drastic situation supported and required for Italian school to go in deep in indoor air quality control and monitoring solutions. Regarding the model, or when all of the data has been collected, with complexity in any case, and several survey and positioning in the model itself, we have developed different typology of dynamic modeling for Energy Plus. In this specific case, the school is very big, so we have one model. In all of the cases, we work at one room, one zones, a starting point, because all zone has been also monitored, at least in terms of temperature and minimal, you can say, values and inside them. After that, clearly, we are working for model simplification solution that passing from multi-zone to simple or few zones models. In addition to that, for very large model like this one, till we will work in simulation in semi-real time, so detecting, for example, the performance gap for the last hours. What we also had is a simplification process, maintaining the zone, the room zone connection, splitting the model in parts with a sub-calibration for making also this simpler and shorter model working. This is reason is the time used by the server to run Energy Plus. So let's consider the surrounding building, let's consider different type of profiling, so standard European one till standard modified after the inspection, in order to have different typology of possibility to detect the performance gap, not only on the standard user profile, but also the standard adapter. For example, school pupils in Italy is a different time scale with respect to the Italian, to the European 16798-1, the standard scheduling. Considering the monitoring, in addition to clearly precision and accuracy requirements, we also had other specific system requirements connected to the E-DYCE implementation, which is the need to use commercial available solution, not producing our own, if possible with Raspberry or something, to use a scalable modular architecture. So adding more sensor will not be problems in terms of this architecture in itself. The possibility to have access remotely to the data in real time or almost real time. That may be also complex for several solutions, and also the possibility of preventing data losses as much as possible. So we have, for example, storage capacity at the data logger base, storage capacity at the gateway base, storage capacity in the cloud from the company that provide the sensor, and storage capacity in the Fusix servers and in the Polito server. The system is working also if internet connection is lost for some of the moments. It's only important that the data logger is working, and we will, after, immediately when the logger is coming home, it will repurchase the data to the server. The storage capacity is also quite large, and we also have the possibility to avoid and fix the fact that we can install sensor without plan, because you can imagine to go to residential housing and say, I have 30, 40 data logger, and I will get you all the plug in your houses. No one will accept these type of situations, and also it's very costly and very complicated to the user to have the permission to do that. So we go to a solution that works in all of the loggers with battery, with the exception of the external CO2 sensor and of the gateway, which is the only elements, one full building that use plugs. As you say, the gateway, if it lost the connection or the plug, is not a problem for that. It's also working for a cost-benefit ratio, because they are very expensive solution on the market. We work for one which is sufficiently low cost, and also include a maintenance cost which is not so elevated in terms of cost of the cloud server provided by them, and also by the maintenance costs in terms of battery exchange and so on. We're also looking for high security in the cloud connection, because some of the users, especially the houses, are not so happy if people may enter in the servers and etc. So we have done self-communication solutions searched, and also the possibility of having SIM-based gateway, which is independent by the local network if this will go down. What we monitor is temperature in all of the conditions, temporal relative humidity in not so used rooms, temperature relative humidity and CO2 in all of the classroom and all of the main used spaces in residential. In some cases, we have external degree days sensor to see the local changes in external temperature And also we have electrical consumption. In the majority of the cases, this is only a reader of the pulse on the electrical meter, so we do not have captured the electrical system. In the school, which is very large, we also have installed a more complicated heat consumption solution, electrical consumption solution. After we have the heat flow meter installed in all of the cases for the heating consumption. As said Pierre, and I'll say also by Tristan, this is not so easy to be installed because we need to cut the tube, so we need to be in a moment in which the season is not the heating one, and so on. We have one external CO2 probe, some illuminance probe, and some total Vogt probe. The state of the window sensor with 3 with battery is not the best solution because the battery needs to be changed too many times to be cost available in terms of replicability. We, after having all of this sensor installed and the data provided, we supported a model calibration approach using the PREDICE tool that has a sort of scenario that simplify the calibration process thanks to sensitivity analysis with minor changes in input parameter of the model that we select at the beginning, like few ranges around the U value, some variation of the roof U value, for example, or especially of the data that we don't know. So for Windows, we have an idea in some cases, in the other, we only have looked at that. So we may have a small range of variation in terms of U value, solar rate, transmission, and etc. That's the approach. For a couple of weeks or 3 weeks, in some cases, we use the monitored data, we align them. We align the simulated data with the monitored one for the calibration. When we reach a sufficient accuracy in this case, we test the calibration without change the model against in the other period monitored. So we have now 2 years and a half monitored data. And as you can see by this graph, the monitored approach is fully following the building profiling, even in the other period. That is done in all of the cases for temperature. For the school, we also work for CO2, but CO2, we are able to detect the general trend and not the local specific peak. The work, so the fact that the model may follow in real time and semi-real time, the monitored data is something that we reach at a room level. In all of the building, clearly it's easier to reach the general building behavior, the average one, because the calibration efforts are limited in this case. If we go to room level, we will see that potentially we need to recalibrate or rearrange some of the aspects. So this will be very time consuming. We want to have this precision. But clearly, if we want only to have, for example, heating consumption, profiling calibrated, or general trends in thermal comfort, this is fully achievable with a single average building calibration process. So I thank you in this sense. And I leave the line to our external guest, or to Nicola, if you want to represent again. Thank you.
Good morning. Can you confirm that you see the screen well?
Yes, we can hear you, and we can see the screen.
Okay, very good. So first of all, let me start by thanking the E-DYCE project for inviting Sato to present his, let's say, point of view on this monitoring buildings problem. Then also good morning to everyone that is in the webinar. So let me, before going into the monitoring aspect and how we approach it in Sato, let me just go and let's say present the idea of our project. We have 16 partners in 7 European countries. Our project will end in September 2024. We are more or less halfway to the implementation. We have 9 pilots that are distributed in 3 different climate zones. Let's say warm in the southern Europe, in Iberian Peninsula. We have more moderate pilots in Italy, in Milan, and then colder climate pilots in Aalborg and also in Austria. what is the challenge or the main motivation for, and this was the reason, actually, it is the challenge that is raised by the call that we applied to, is the fact that homeowners and building managers are currently, to a great extent, not able to assess the energy performance of their buildings, and this is a common problem that is shared also with the E-DYCE project. So the challenge here is to develop tools that enable the assessment of the performance of the building and the equipment that is inside the building. And how did we approach to overcome or to answer to this challenge? So we set ourselves to create an IT platform for automated self-assessment and optimization of buildings energy. And the idea is that, and it was actually something that our project officer made as a very serious objective when we were discussing with him, is that we should be able to provide real life assessments from the building, from the devices, from the systems that are installed in the building. So that there is a focus on this real life utilization of energy, let's say. This is our main objective. So we set ourselves to build this IT platform. We conceptually, but also at the implementation level, we organized it in 4 layers that we try to make them as independent of each other as possible, because this allows us to achieve different deployment strategies. It also allows us to make the platform, this is something that was already pointed out in one of the presentations, we can also enable third parties to write services or assessments on top of our platform. And the 4 layers are the ones that you see here. We have, let's say, a middleware at the lowest level, which will be the focus of the remaining of the presentation, because it's related to monitoring. On top of this middleware that interfaces and monitors the building, we have a self-assessment framework. It's a layer of knowledge extraction, if you wish, towards the assessment of the building performance. And then using the data and the knowledge that was extracted in the form of KPIs and assessments, a number of services can be developed to actively, or with recommendations that will help, let's say, managers to manage the energy resources in the building. Of course, the last layer is the application layer, where we have different kinds of interfaces, mostly BIM and web-based, but also the web-based interfaces that we are developing are also compatible with mobile devices. So let me go into the monitoring direction. From a technological point of view, we have a few challenges to address. And one that is really related to monitoring is the capacity of integrating a growing number of devices that are very heterogeneous in their interfacing, because they have different protocols, they have different data formats. So sometimes it's really a challenge to bring everything together in a consistent way. Then, of course, and this is thinking of data sharing, which was something that Pierre from NeoGrid already pointed out. We should model the devices from a semantic perspective with the required properties and features of these devices, so that we can have higher degrees of interoperability, not only within the requirements of our platform, but also when we share data with others. We should share not only the data, but also the meta information that allows interpreting this data and use it in an automated way by machines, let's say it this way. And finally, because we want also to automate the processes of assessment and optimization, we need to exploit this semantic information. And we aggregated, let's say, in what we call a context information model. Okay, I will go a bit deeper in this aspect because it's related to monitoring. So what are now focusing on the monitoring aspect and on our first layer of the SAPO platform that we have been developing. Maybe it's the component of the project that is in a more advanced way of development. There are two main functions that this middleware needs to answer, which are the provision of monitoring and also actuation capabilities. That's the way that then the services can actively change set points, open or close windows, decide some energy flows that will happen within the building, etc. Now, if we look at monitoring mainly from a data provision point of view, nowadays we need to address issues of IoT connectivity, like data endpoints, different communication protocols, different data formats. This has all been mentioned in previous presentations here. Now, if otherwise we think of monitoring from an energy management point of view, if we think that our monitoring is mainly geared towards facilitating energy assessment and energy management within the building, there are additional requirements and additional information that must be monitored, not only the physical quantities, let's say, that we need to measure. So data has to be automatically integrated. Therefore, let's say a single format should be used within these platforms that we have. And we should also export and share this data with third parties as we need in a, let's say, standardized common way. If we have sensors that are from different vendors, ideally, we should not share this data further with third parties. One sensor in the format of the vendor of that sensor, and then another sensor in a different format. We should aggregate the data together, describe it, and provide it in a single coherent way. If we want to do active management, of course, we need to provide interoperability to different systems. I'm talking about the control part also. So this is also a requirement that we can interoperate with systems that were not made to operate together, okay? And we need services to integrate them. Then the relation of data with systems, building components, or external data sources has to be established. So for energy management purposes, we need to know that a given sensor is in a given room that belongs to a certain assessment zone in a given building. If we are building platforms that can address the management of different buildings and different zones within buildings, we need to structure and to model also this information. And actually, we also need to monitor. If we change a sensor, this should be reflected in the information that is in the platform, so that we don't keep using that sensor information for a purpose that it's no longer serving. So monitoring goes, I would say, goes a bit beyond than monitoring the physical quantities. It also has to be related to the different relations with data to systems and to building components. So this is, of course, related to the hierarchy and relation between the systems, the building components, and other sources that has to be established. We need to know if a sensor is installed at a specific part of an air handling unit or an HVAC system. All the details that are related to the operation of these devices. And I'm using sensors as an example, but this extends to other systems that are installed in the building. So what are the requirements to fulfill all these let's say expectations that I was mentioning about to extend the monitoring? We require this single format for data integration, systems integration for interoperability, and then the relations between all these objects, just to summarize this point. What has been the approach within the SATO project? The picture that you see shows, let's say, a high-level architecture of the SATO middleware that we are developing. Now, I'm not going to focus too much on the aspects of the physical devices. Of course, we share the experience that has been provided by others, where we have some difficulties sometimes with the physical installation of devices to guarantee that they are working. There have been also problems requiring the acquisition of the systems because of scarcity that has been pointed out also. So I'm not going to let's say extend further these concerns, and I'm going to start by the beginning here, where we have the buildings and external data sources that are providing data already, and all the information enters the platform through entry points, let's say, that can receive specific different specific protocols that are used. So we need to have let's say an interface, that we need to expose an interface in the platform so that the systems can reach this platform. And of course, these have to be compatible with the range of protocols and systems that are inside the building. We want to build, from a monitoring point of view, SATO is agnostic to the different vendors, to different providers of sensors, different providers of systems operating within the building. So, and this is actually a feature because we want to be able to integrate different data sources, different data formats in a consistent way. Now, we then already inside the platform, all the data that reaches the platform, we are adopting a streaming approach, which means that upon arrival, all the information is immediately sent to the required platform components that should receive it, okay? And of course, these first components, as I will explain, will be those responsible for integrating all the data, having it normalized to a standard format and so on, so that then it can be properly shared or integrated within the services that we are considering. Now, the relations between the systems, the fact that we need to know if a sensor or an actuator is located in a room that belongs to a given zone, so that we can, let's say, aggregate all the information within a zone of the building. These are established in, I already used the name, in a context information model. And this context information model is implemented in the form of a knowledge graph, okay? Maybe some of, all of us, or some of us know graphs from mathematics. That's the representation that we have. All the physical components are represented as entities in this knowledge graph. All the sensors, all the quantities, all the systems that we have, all the zones, all the rooms. And these are the nodes of the knowledge graph. And then we have our connections between these that establish the relations between them. So a sensor is contained within a room, is contained within a zone, and so on. So every relevant building component and system has, let's say, a virtual counterpart within the platform that holds all the data, the physical measurements that we have, the quantities, that's the basics. Or if it doesn't hold the data, it knows the way to access the data if it's in a different database, for instance. It holds all the properties, all the information regarding to that actuator or to that zone or to that sensor, and also the relations to other systems and components within the building, okay? Now, one of the software components where this information is sent upon arrival, as you see in the picture, is the syntactic interoperability module. This is the one where we make a translation between the different data formats to a common format within the platform. That's where we aggregate into a single coherent representation of the data, okay? So it then, let's say, a data point becomes, after these first layers here, a data point becomes more than the measurement or the result. It becomes part of a device in a room, in a zone, in a building, because it has been integrated into this knowledge graph in a way that puts it in context, let's say, within the building. Now, what are the main challenges to address this part of monitoring? One, getting and maintaining the semantic information and the knowledge graph updated. This is also, of course, very important. And in SATO, we believe that BEAM and IFC files should be the right way of providing and updating this information, okay? Then we also have the challenge of keeping the syntactic interoperability component updated regarding updates in the received data format. For instance, a firmware upgrade in a sensor that is in the building might change the format of the data, the way the data is organized in the messages that are being sent, and we need to accommodate this change. So this is also a challenge because sometimes it happens in practice. You start receiving data in a different way, and now your receiving module doesn't recognize how to extract the important information that is within. Then, of course, there is the diversity and arbitrariness of existing data formats. There are too many different vendors use whatever they wish. There is already, let's say, things are converging to some formats. And then maybe regarding the context information model that I was talking about, there is a lack of semantic annotation standards. And those that are already doing it, it seems that different vendors, each vendor wants to develop its own, let's say, ontology approach, its own semantic way of describing the systems. And this needs to be also overcome. So how do we do this in practice? To organize all this, this is a really difficult picture, I know, that you're seeing on the screen. It's very complex, but it's the actual and the concrete implementation of the previous picture that we did. It shows the low-level architecture of the SATO middleware. I would ask you to focus on the thick red lines. It's the let's say what we are going to approach here, so that you understand from a monitoring point of view, how do we take care of the data that reaches the platform before it becomes ready for the actual assessments and services that integrate all this data. So we are receiving data either from specific devices directly from the building, such as Shelly or other off-the-shelf devices that you can get in the market. We also receive it from gateways that are within the building, and the gateway already aggregates the data from the whole building and forwards it to our platform. Or we are, and for instance, an example, a practical example that we use in our pilots is that we interface with the gateway from the Siemens, the Zigo CC platform. And we, gateway in this case, sorry, not platform. Of course, we also integrate with third-party platforms. In our pilot, we have 3 of them at least, that these platforms receive the data from the devices and then forwards them to our platform. So 3 different integration methods that we have running currently. In some cases, we also have to do web polling. So we don't, the systems are not sending the data to us. We have to fetch it somehow. So we have these 2 components that are highlighted in yellow there, which are able to receive all the data that is being forwarded or are able to fetch the data in a polling manner. Now, once the data arrives to these, let's say, connectors that receive the data, we use a broker, a data broker, a streaming data broker that is called Apache Kafka. We chose it because it's an open source already, an open source tool that is highly adopted in real world distributed systems and which have high degree of scalability. That's why we chose it. And this is our core component. So it receives data from the exterior and also manages the communication within the platform components. So data is received, if you see in this red light, this second yellow circle is what we call the Apache streaming, Apache Kafka streaming component. Then it goes to this data catalog component. It's the one that is responsible for translating the different data formats into a common format that is received within the platform. And then it keeps going on, goes to this, it can go actually through data quality checks to see if the data is okay. It can, the data can be augmented with information from the context information model, if this is relevant. And then it goes to a data structuring module that prepares the data for the actual assessments and for the actual services that are ready. So this module gathers the data and prepares it in databases already in the formats and the structuring that is useful for further processing within the platform.
Pedro,
yes.
could I interrupt you because the time is running?
Okay. So at least here I was reaching the end of this part. So this last yellow circle that I have here is what we call a federated storage system, where we have different kinds of databases according to the purpose that the data is meant to serve. Let me move quickly to the next slide, and in a couple of minutes, I think I can finish. This is what the layer that we have above the middleware. It's the one where all the assessments and KPIs are being calculated. So they connect to these structured databases that we have, where the data is aggregated and prepared. So after all the monitoring stages, the data is there, aggregated and prepared for these assessments. And I would like to emphasize the importance of the context information model, the semantic modeling, because it is the one that allows us to automate these assessments. If I know that 2 sensors are available within a given zone, I can launch certain number of KPIs. If I know that certain energy meters are installed within the building, I can launch certain KPIs and assessments for whole building energy assessment and so on. And this is actually automated within the platform. So the manager doesn't need to do this manually, I would say. Just to wrap up, then the assessments that we do with all the data that we aggregate from the monitoring stage, we have all building energy assessments, building envelope assessments, occupant-driven assessments. From a monitor point of view, we are also monitoring the occupancy of the building, besides the typical physical quantities that were mentioned from in other presentations. Also, the external environment is important because it is a perturbation for the building, and the assessments also take into account the occupancy and also the external environment when this is relevant. And then we have also assessments for building systems and in the residential sector for specific household appliances. These are the categories of assessments that we apply. And then the services, we have the assessment services, of course, for visualization of all the assessments, KPIs, and so on. Aggregated control that can control different devices within the building simultaneously for user comfort, flexibility, and to manage specific systems and building components. So thank you for paying attention. And again, thanks for the invitation to present here. If you have questions, then after we can answer them. Thank you.
Thank you, Pedro, very much for your presentation. We are running a little bit behind the schedule, and we have still one presentation from Dimitros in our pipeline. So Dimitros, the floor is yours.
Yes, can you leave the floor to me, Pedro? I can't share my screen.
Okay. There you go.
Just give me a second. Can you see my presentation?
We can see your screen. Maybe maximize the
Yes.
presentation.
Thank you. I'm Dimitris Lokas. I'm a Research and Innovation Project Manager in Core Innovation Center.
Dimitris, sorry, it is not scaled to the Zoom. So now we see it in a strange
in editing mode.
It's in editing mode.
You should click in the presentation icon that is to the left of the Zoom slider, down in the right lower part of PowerPoint. Yeah, that one.
It's okay now?
No,
it's not. I think you shared the wrong
window.
Maybe,
the
yeah.
wrong page.
Now? We had the same earlier problem. It's with the Zoom. Anyway,
go back to the previous, exactly, and work
yeah,
this.
I
Maybe.
will. Yes, this may be better. Yes, sorry for that. I'm a research innovation manager in project in Core Innovation Center. I have a master in civil engineering and IoT and smart system. The scope of this presentation, I try to be quick because we are in time constraint here, is to discuss the Core Innovation Center hybrid cloud infrastructure in E-DYCE project. This, as speakers have already said, we have all the data from the monitoring of the sites, but the main purpose of this monitoring data is also to have a forecast of some physical values like the energy consumption or the weather. The topics about this presentation are the historical data collection, which is very crucial for the deep learning models development. I will tell you about the inference core model environments, how our data science create their modeling, the model output and the protocols used where we can share our forecasts with the partners for their modeling also, and also the cloud service communication and connectivity options. First of all, this is our general core hybrid cloud infrastructure. Here we see the general layout. It's a weather service example where we will discuss earlier each steps of the development. In the first phase, we all get the data usually from some data sources. For the weather physical data, of course, we use some paid services, or we can use also the weather stations data, which are located in each of the pilot building. The data comes to our weather batch topic, to our top local database, where we collect them and we can do exploratory data analysis and data cleaning, and we store it by the time in a time series database. This is a third part. It's very crucial. I will talk about it later in a different slide. It's crucial because the weather takes and all those values for the development. We use the deep learning models. We need the data at least for 4 seasons a year, especially for energy consumption and weather. The next part is the model development phase, where we see here that except the first step, we also have employed the creation of the model part, where we have inference weather servers, the ML models, which are created by our data scientists. And there is an inference topic where we get the inference output, and still we have the real-time data flowing through the data sources, which are then compared, and the models are further developed and optimized. And the last part is where we use the inference distribution server. All the outputs of those forecasts, the forecasts every one of our partners needs, are pushed to the middleware, where we can, where then everyone can get this data in some simple or more a complex format. About the first step now, it's the historical data collections. In the E-DYCE project, we have the weather forecasting and energy consumption forecasting. Here we see that we have all the different pilots, which are the Nicosia, the Torre Pellice, Geneva, Aalborg, and of course we can add more later. Here in this part, we have to gather the data. We gather data in complete different databases for each pilot. We can also add other pilots after the project. The system is fully scalable. The persistence of the data, it's very much given positive for our work because we can keep that data for future access and developments for each of the pilot site. We have multiple database options. We can use Mongo database or InfluxDB. This has to do with the nature of the data. For example, if it's time series data, or if we use data which are not constrained by time variables. And also another good thing is we have remote access because the data is in core IC headquarters, where we have a fail-safe storage database, and we can access from everywhere since we have a very good line to the internet. And the visualization options, all this data can visualize at any moment from our scientists or outside partners with Grafana. The next part is, of course, the main part is the inference core IC model. It's all where the modeling takes place, where we have the APIs, the internal APIs are constructed. As for the E-DYCE case, we have a weather and an energy consumption API. Here in this schema, you can see the correlations between those in this particular example and the E-DYCE project. We also get some insight from the weather API, the weather forecast, to increase the optimization of the energy consumption. In other projects, that's why I'm calling about the inference core IC module, that there are some modification for each project. We have a neural network inside here in the middle, where let's say the insight we get from the one API or the other can focus and improve the modeling of the other. This everything of course can still be watched in real time with Grafana dashboard or any other dashboard. The main, let's say, scope of the modeling is to consume the data streams produced by the data acquisition pipeline. Then we apply the necessary data pre-processing, prepare the bus to be sent to inference, and then generate the predictions. So here we have some node characteristics. We use NVIDIA Triton Inference Server in Docker imaging, and it's a RESTful architecture for every one of the technical here staff which knows about this. And we have, of course, real-time dashboard visualization, and it's scalable. So meaning a lot of people can work at the same time. So this is the final, let's say, implementation. We see here for weather, the same is for energy consumption about the E-DYCE. It's the final part where we have, I have to say, 3 different forecast horizons. We have short-term forecast, mid-term, and long-term. This is 24, 7-day, and month ahead. And here we see that when everything is developed and we push data to the middleware of our project, everyone can get the forecast for each of these forecast horizons. And the next slide, we have the forecast seasonal models. Here we have 2 Nicosia examples, how the data is shown in dashboards, and the partners can have access to them. Here we see the deviation, the top of the temperatures and the minimum of the temperatures in a 24th month period. So everyone from our partners which are developing their own models for the buildings can get the necessary input and towards the dynamic EPC of the buildings. Also, there's a short-term forecast here, which is a day 24-hour ahead for Nicosia. Here we see the 2 lines, which is how close our forecasts are to the real values, which are the yellow line and the green line. And lastly, I have an energy prediction also forecast. This is for the Aalborg building 4. We have, let's say, the future of the daily thermal error here, who has of course some value to our data scientists to construct this energy prediction, because you of course have some deviations in that. But here we see the last predictions, which are the upper bound, the roll bound of the future forecast for energy consumption of the building. This is of course very crucial for modeling of the DEPC, and all this data can be taken as input for the modeling of our partners. Also, I have to say that our core hybrid cloud infrastructure is very much compatible with all known state-of-the-art and wide-established communication protocols and individual services structured upon those interfaces like MQTT, Kafka, REST API, and the rest. This is all from me. If you have any questions, feel free to add them to the chat. Thank you.
Thank you, Dimitris. And that was the last presentation for today that we have prepared for you. We, as you can see, we are running behind the schedule. I could see there were some questions in the chat that some of them were already answered actually in the chat. So you were very efficient by talking to each other while the presentations were running in parallel. I think there was one question actually from from our colleague from the project, which was about monitoring. So going from no monitoring to course monitoring, let's say per year, through something like a middle monitoring frequency monthly up to a fine frequency monitoring, so hour and sub-hour monitoring. So what was the added value? What is the added value of doing so? I think this was the main question was after the Pierre has presented and Tristan. So maybe you could shortly elaborate. I know you already wrote something in the chat.
Yes, I can start, and I guess Tristan will complement.
Yeah.
I guess, as Tristan was pointing out, the key issue there is feedback. If you have yearly data, then you can only get feedback on a yearly basis if you use your data for feedback. Essentially, going from no data to very coarse data at year level, you already introduce some possibility of catching some of the issues. It's important to keep in mind that when you have no monitoring, essentially the feedback on problems in your building comes from two sources. One of them is strong discomfort or like very visible issues. And that's basically a very strong deviation from your usual performance. And that's typically just the worst cases that are found. And pretty much the same on billing. If you're looking for sort of 10 to 20% improvement on your performance, so to speak, that's not something that you can find without sensors that easily, unless you have like technicians running around the buildings and doing manual checks. But that's typically not how we are looking at it. You of course also have regular inspections when you have maintenance contracts in the buildings, but that's a different kind of service, and it's also something that happens maybe once a year or every other year. When you get from yearly to monthly, you don't necessarily get that much extra information. You might get a bit more feedback, but it's quite limited, and it's because the weather varies a lot from month to month, so you can't just compare, for example, August with October. So that makes it trickier as well. You would typically want to compare an October month with October the year before, so your kind of feedback there is not getting much better. Daily brings significant improvement possibilities when it comes to analyzing both indoor climate and energy demand in office buildings and so on. You can typically spot differences between weekends and weekdays and start seeing if some of the setbacks and so on were not implemented. In residential sector, it's a bit trickier on that level. But essentially, I would say for me, the gold standard is what happens when you start getting hourly data, because then you get very sort of fine granularity in your data sets and good visibility on what's happening dynamically in the building. So that would be my recommendation, specifically in terms of measurement points, energy, both in terms of electricity and then centrally in the heating production of space and water in the building seems to be a must. And then at least one indoor climate sensor with at least indoor temperature per apartment would also be very desirable.
Yes.
Yeah, I'd just like to add something there. I think the monthly comparison adds. I mean, you do not need to compare 1 month with the same month of the previous year. You just need to be in a month of the heating season or cooling season, depending on what you're interested in. And mainly you could compare 2 months that are following one another, and knowing their the weather within the 2 months. So you still get a smaller time of feedback with the monthly data, but I agree that the must is definitely hourly data. But just to outline the fact that if you get monthly data, you can still get a feedback within 2, 3, 4 months of heating or cooling season, depending on your focus.
Yeah. Also, on top of this, what you said, we can see actually that you can supplement your, let's say, observation from different sensors or meters that you have. Sometimes the data is corrupted or there is a lack of sensor of one kind, but you can actually come to a conclusion by looking actually at the palette of the monitoring points and parameters that you get. So once you have energy, temperature, CO2, window sensors, you don't need at the same time 4 of them, maybe, if they drop out, but you need some of them to have actually a picture of if the building is operated as expected or if it's drifting away. At least this is our observation based on the data analysis of the data that we get from the Danish demonstration cases. But still there is this expert element. So this is not fully automated yet. You need a human there in the process to do some of these analysis and to do the, let's say, the subjective assessment of what is happening in the building.
Maybe just an addition to that, I guess when we look at dynamic EPC, it's important to remember that our aim is not necessarily to fully replace the human in the certification process, but more to sort of pinpoint the points or like the places where human intervention is going to be most effective. It's because a lot of the discussions in the AI space comes with the concern of replacing humans, but that's definitely not what we are thinking of here. It's just ensuring that we use those human resources, especially in Scandinavia, where they can be very expensive, sort of for to generate as much value as possible.
Yeah. I know we just passed actually our time by 4 minutes. We had also one more question from Aliki. Maybe very quick we can address it. It was about the main challenge per speaker. What was the main challenge to overcome that you have experienced? One.
As I said in the chat, mostly the interactions with all the people engaged in the building, going from tenants to the owner and to the building manager, both managing the tenants' contracts or even managing the energy, the technical installations. And all of these people, you need to centralize information and communicate through all of them, how would you say, smoothly. And this is very time consuming, even more when it comes to tenant, because the number of tenant, of course, is way higher. But yeah, this increases even more when you add more case studies. And this was very unexpected on our side, at least at the beginning of the project.
Yeah.
And for the Danish case, it's basically the same input because we were centered around the residential sector.
Yes. Giacomo, do you have something to add on?
No, I agree to the fact that is interaction in between the involved, we can say, companies or the demo provider or I don't know, tenants, or even the keeper in the case of the house and the school and the technical installation people, because clearly we cannot cut the tube of people without passing by a specific panel or by the panel or by the company that already is working for the school, no? Because clearly there is contract, there is this aspect to be taken into account. On our side, the other, in some way, unexpected aspect is the complexity of finding a commercial solution on the market with a cost quality which is in the correct line. No, So it's a bit for us, at the end we solve them, but it's a bit complex for us, the idea that we were waiting that, okay, smart building is everywhere. So in some way, commercial solution for this type of monitor is easy to be accessible. In reality, it's not so that, especially when you go not with a, I don't know, when you pass by the domestic sensor buy by people on Amazon to something which is not done for that, may also do that, but is mainly conceived to manage the building. And that's especially when you look for indoor air quality, this type of solution, the market is limited, or at least the cost benefit is very complicated. And to find solution is not so easy. To find solution working on cloud, with open cloud, for example, is also another issue that we have faced, with the possibility to avoid, or at least at the beginning, not having the idea to reduce data losses to the much as possible. We're not looking at problems of filtering, no? But the fact that, I don't know, internet is missing, we lose 1 month of data, something like that. So it's basic things, but it's something that take more time than expected. I think also the other potentially may face something like that. Potentially not Pierre, because they are your own solution, but.
Totally agree with that. And also the data quality, depending on the monitoring you choose. Sometimes you ask someone to install a monitoring because you pay them and then they install it and they do not check if the data is actually working or anything. So
Yes.
there's no control on the data that's transmitting once it's been installed. And this is a huge issue because it takes a lot of time to just to check if everything's working well and to check it over time.
Yes, and as for forecast development, also I have to add here, as Tristan said, that because we need at least 1 year for seasons of the data, there's sometimes some gaps in the data, and that's very much very lingering for our work. Especially we have to have this data at least at the time the project is running, so we can provide the forecasting for this in real time and optimize it. And also the same about the consents. Sometimes we don't have the consents of the tenants, so we have to, we can have its energy consumption from each of the apartments of the building. That's caused some issues, but everything goes okay now.
Yes. Pedro, do you have something to share with us, your main challenge from your project?
Well, I in some of the buildings, I align a lot with what Tristan said. Lots of difficulties to have things installed and checking that they are functioning, and so difficulties with people that manage the building. But then there is one which is a concern, and probably this happens in other buildings too. Buildings that have multi-tenants. And then the GDPR becomes really an obstacle because you cannot get all the data that you need for integration, because some of the tenants agree with sharing the data, some others don't agree. And then, let's say, at least for more detailed assessments that can be done, this is really an obstacle. I'm not sure how to overcome it, because suddenly everyone is afraid of sharing data. I understand personal concerns, of course, but some of the data that is required is not really too much. If used in an aggregated way, it's not really a problem. So I think there is really a big challenge in security of the data and trustworthiness on the systems. Somehow we need to develop the systems in a way that people perceive them as trustworthy, so that they feel comfortable in sharing the data, so that all the platforms, all the sophistication that we are building can actually work. Because without the data, we have nothing, to be honest. All of what we have been talking about is data-driven. So security and trustworthiness are two keywords for me that we need really to address in the near future in these kinds of platforms.
Yes, I think we should now close the webinar. My also maybe final conclusion from this is also that, well, in the existing building, it is as it is. So we have to fight our fights. but maybe we could do something better for the new build buildings, so that they are in a way in a better position, prepared for the future activities related to the assessment of these buildings. And here what I mean is that if there is a monitoring system to be included, then it is designed according to some standardized solutions, so that the data format is in a way predefined, the protocols are regulated, etc. So my conclusion is that probably for the new buildings, we need some kind of regulations, and we need probably some rules from above us scientists, given by the regulators, how this should be implemented in the buildings, so that we do not continue having the Wild West situation that we deal nowadays. This was my final conclusion from this webinar. I hope you enjoyed the presentation. There was a lot of value in them, and a lot of real life observations, which I hope will be taken further and developed further in these projects that we're running, or in the next projects. So thank you very much, and I also invite you to the next webinars that we will organize. We have 2 more in our pipeline, so we will post that on the social media when we will approach the dates. Thank you very much. Have a good day, and thank you for your contribution. So to all of the speakers that prepared the material for today.
Thank you.
Thank you.
Thank you, everyone.
Bye bye.
Yeah.
Thank you,
Bye-bye.
everyone. Bye-bye.